Hi there, and welcome to today's session on work, energy, and power. My name is Heinrich, and I'm going to be walking you through some key concepts today to help you understand and excel at this particular topic. Now, when it comes to this particular topic, I would say that the first place to start is to make sure that you understand forces and components of forces, because you are going to be applying those concepts a lot in work, energy, and power. So make sure you understand forces and components of forces and free body diagrams and those very basic things that we need in order to do kinetic physics, right? And then once you've got that under the belt, you can actually quite easily do this section. So let's get going. Okay. Now, the first thing I'm going to talk to you about is the conservation of mechanical energy. Now, the conservation of mechanical energy is an incredibly useful tool when we are in an isolated system. Now, in an isolated system means there's no external forces like an applied force or a frictional force or anything like that. And it is only in an isolated system that our mechanical energy is in fact going to be conserved. So what on earth is EMEC? Well, EMEC is the sum of kinetic energy and gravitational potential energy, EK plus EP. And if you like, you can also write that as half mv squared plus mgh. Okay. So if we're saying conservation of mechanical energy, we're meaning that mechanical energy has to remain the same, right? So that means that for some motion of an object, if it's in an isolated system, the initial mechanical energy is going to be equal to the final mechanical energy. And these calculations are actually only useful if we do have a change in the vertical position of the object. So if the object didn't go up or down, then the left-hand side and the right-hand side is not going to be a particularly interesting equation because the EP part has to remain the same if the height is the same. And then if the EP part is the same, the EK part has to be the same. Okay. So usually there's going to be some sort of change in height, but this EMEC initial would then be half m times the initial velocity squared plus the mghi, right? So that's now the initial mechanical energy, and that would be equal to half mvf squared plus mghf. Okay, so this is the formula that we are most likely to write down and to use if we are going to be applying the conservation of mechanical energy. Now, another important thing that we understand is what they mean when they say at a maximum height or when it's going at its fastest, right? So when we have a maximum height, okay, that is going to be when the gravitational potential energy is at a maximum. But since the mechanical energy is the sum of kinetic energy and gravitational potential energy, in order for gravitational potential energy to be as big as possible, kinetic energy has to be as small as possible. And the smallest that it can be is 0. So in order to find the maximum height, we usually go and put the kinetic energy as being equal to 0 in our equation, right? And then if we're going to be talking about the max speed or the max EK, well, now it's the opposite, because if we want the kinetic energy to be as large as possible, then we've got to make the gravitational potential energy as small as possible. And so when we're talking about max speed, EK is at a max, and that is going to be when the EP is at a min. So, you know, when it can't be further vertically displaced. So we usually have that as EP equals 0. So that's when the height is going to be 0. Okay, so let's look at an example of how to apply this. So we've got a 2 kilogram crate and it slides up a frictionless incline. Now here, there's some clues, right? So when they say things like frictionless incline or smooth incline or something like that, they're trying to communicate something to us. And it seems obvious to say, yes, what they're communicating is that there's no friction. But what they are trying to tell us, in this case here particularly, is that we're in an isolated system. There aren't external forces like an applied force or a frictional force. It's an isolated system, and that means we can apply the law of conservation of mechanical energy. Now, it says at the bottom of the slope, this crate has a velocity of 5 meters per second. And then we want to know what the crate's vertical height is going to be when it's moving at 2 meters per second. Right, so for this question A here, we're going to use the conservation of mechanical energy because there is a vertical displacement. We want to know how high up it goes at the time that it's moving at 2 meters per second. And we are in an isolated system. So check and check. So let's see, if we do our half mvi squared plus mghi, that's got to be equal to half mvf squared plus mghf. Okay, and then we can just substitute in, right? So this is going to be a half, the mass is going to be 2, the vi squared is going to be 5, and be very careful to make sure you always include that squared there. I've seen many crocodile tears because you forgot to put the squared in your calculation or in your formula. Right, so then plus the 2, which is the mass again, times 9.8. But then the HI, well, it looks like this is basically like on the ground, right? So we're going to make that 0. So that term there, we're not really going to worry about because, well, anything times 0 is just 0, hey? So that's then equal to half times the 2 times Vf squared. Now, Vf squared, they tell us, is the 2 meters per second, because we want to know what this is, the vertical height, when the velocity is going to be the 2 meters per second. So I'm going to make that 2, I'm going to remember to square it, and then it's plus 2 times 9.8 times this HF here. Okay, and now we're golden because this is actually not too complicated an equation to go and solve, because we've got the 0.5 times 2 times 5 squared, that's going to give you 25, right? And then the half times 2 squared is going to give you 4, and that's plus 19.6 HF. So then we just have to go 25 minus the 4, which gives us 20, which is then equal to the 19.6 HF. And then we're in luck, we just go 20 divided by the 19.6, and we get an answer of 1,02 meters. Okay, so what does that mean? That means as this thing's going up the slope, at the point where its vertical height is 1,02 meters, while at that point this object will be traveling at 2 meters per second, right? And I'm sure we all know from our experience living on Earth that as things go up a slope, they tend to slow down if the only force acting on them is gravity. So then we need to find out, well, what is the maximum height that the crate reaches? Now, again, if we think back to not too long ago, somebody said something about the maximum height must be where the gravitational potential energy is at a maximum. And in order for that to be the case, well, the kinetic energy has to be at a minimum, which is 0. So maximum height, kinetic energy is 0, right? So I'm going to do the same thing as before. Half mvi squared plus mghi is equal to half mvf squared plus mghf. Okay, and now the half mvi squared, I'm just going to use the same point here. So it's going to be the half times the 2 times the 5 squared. And now here I know that the h is 0. So I know this whole term is going to be 0. So I'm just going to go plus 0. And then here I know that at the maximum height, the kinetic energy has to be 0. So for that half mvf squared, I'm also just going to put 0. And then plus mgh, that's still going to be 2, 9.8. And then the HF, which is going to be that maximum height, right? So now all we do is go 0.5 times 2 times 5 squared, and again we get 25, and then we just have to divide it by the coefficient of HF, which is that 2 times 9.8, and so we get an answer of 1,28. So then HF is equal to 1,28 meters. So what does that mean? Well, it means this thing slid up the slope, slowed down, slowed down, slowed down. And then when it was 1,28 meters above the ground vertically, that is when it finally came to a stop, and then presumably slowed back down the other way. But we're not interested in that part of the journey for this question. So now what I'd like you to do is please pause the video and try this example over here. Okay, so let's see how we're going to do this. So you've got your 2 kilogram crate. It's released on a frictionless slope. So again, they're giving us explicit permission to use the conservation of mechanical energy. And we know that it starts at a vertical height of 5 meters. So here the h is 5 meters. And note they say released. So released is a fancy way of saying that the initial velocity is 0. So we don't throw it, we don't kick it, we don't shoot it out of the gun, we just let it go. Okay, so then we want to know what the crate's velocity is when it's at that vertical height of 2 meters. So for this, we're again going to use the conservation of mechanical energy. Okay, and then we're just going to substitute in for what we have. Now here we know that we released the object, so the velocity was 0, so this whole term is going to be 0. And then we know this is going to be the 2 times the 9.8, and then the initial height was the 5 meters. And we want to know, well, how fast is it going when the height is 2 meters? So now it's going to be the half times the 2. Our thing that we're trying to find is this Vf squared, because, well, actually the Vf, because we want to know how fast was it going at that height of 2 meters, plus the 2 times the 9.8, and then the Hf is going to be the 2 that we've got there. Okay, cool. So if you go 2 times 9.8 times 5, you get 98, and then you've got to subtract from that the 2 times 9.8 times 2, right? So I get here that I've got 58,8, and then half mv squared, half times 2 is just 1, so I've just got 58,8 is equal to Vf squared, and then I just have to square root both sides. Okay, all right, so square root both sides, and I get an answer of 7,67 meters per second. Okay, now we know from our mathematics that when we square root something, we have to consider that the answer might be positive or negative, but in this instance here, we do know that the crate is on its way down the slope, so we can just take the positive answer and write down the slope, and we've got no issues with that. Okay. So then for the next one, we've got to find the maximum speed that is reached by the crate. Now we know the maximum speed happens when the crate has reached the ground, right? So that's when the gravitational potential energy is at a minimum, is 0. So you've got still half mvi squared plus mghi equals the half mvf squared plus mghf. Okay. And now the half mvi squared, we know at the start the velocity was 0, so this whole thing is 0. And then we've got the same thing, 2 times the 9.8 times the 5, right? And now that's going to be equal to, and now we're trying to find the maximum speed, right? So the Vf is still going to be what's missing, as it was in the previous one. So half times 2 times Vf squared, but now when the speed is at a maximum, the mgh, the gravitational potential energy, has to be 0. So this is going to be plus 0. Okay, so then we can go 2 times 9.8 times 5, that's 98. And then we just root both sides. So root 98, we get 9,90. And that is going to be the maximum speed that was reached by the crate. So just note there that they asked about the speed. So because they asked speed, we're not really going to bother too much with the direction for that one there.